I think we're going to get started anyway because the first part of it is just review what I did last time about linear logic, and then we'll go into defining the remaining connectives of linear logic. And after I've given you all the connectives, trying to give you some intuition about what these things mean, we'll talk about the computational interpretation via concurrent computation. And then we'll talk about recovering intuitionistic logic, which usually is done with the of-course modality. I might do it a little differently today. So how does linear logic arise? So we have what's called a linear hypothetical judgment. Okay, so these are assumptions, but you must use them exactly once. So we think of them as resources sometimes. And you're trying to prove C on the right-hand side using those resources. Okay. So always remember that it looks like what we had before, but it's very differently interpreted. So an interesting thing is that we don't change, the definition of like truth, but we change the definition of entailment. So it's a change at the level of the judgments. Okay, where we say we want to think about a hypothetical, a linear hypothetical judgment. Okay, and then we define some of the connectives to start with. Okay, so A linearly implies B. The right rule defines this connective. The way previously used introduction rules, because we were verificationists, or at least I am. Okay, by the introduction rule. Here we use the right rule because we're in a sequent calculus. So it internalizes the linear hypothetical judgment as a proposition. So we say A linearly implies B. If with resource A, we can prove B. And then the left rule says if I have a resource, A implies B, A linearly implies B, I can use that once. It disappears after I use it. And how do I use it? Well, I split my remaining resources into two parts. I use one part to prove A. And then, because I know that A linearly implies B, I can then use the remaining resources together with B to try to prove C. So that's the left rule for linear implication. And then the tensor, okay, is a kind of conjunction. Two things must be true in the same state or among the same resources in the same context. So the left rule says if I have the resource A tensor B, I can use that to extract resources A and B separately. So to prove A tensor B, what you have to do is you have to split your resources. You devote some of them to proving A and the remaining resources to proving B. Okay, so that's the tensor. You okay on those rules? Okay. All right. And we also briefly talked about the tests that we apply to make sure that our rules are in harmony. Because when the sequent calculus, they're a little bit different from what we had in natural deduction. So we don't have an introduction followed by an elimination, but what we have is a cut, okay, which is this rule, where A was introduced by a right rule here, and we apply left rule to A. So it's the exact analog, okay, of introduction followed by elimination is a right rule meeting a left rule. And we wanted to show that we can reduce a cut at a compound proposition into cut on the subformula in order to make it smaller. And that was our test that we applied in that case. Okay, so a few remarks here just to remind you. There are no other formulas allowed in the identity rule, which is why? Because we must use all the assumptions. If the delta was allowed here, we wouldn't be using them, and so that's not linear logic. And the other thing, the difference in the cut rule here is in the intuitionistic cut rule. You had a context gamma and you put it into both premises, and here we don't do that. We split our resources, put some here and some here. Why is that? Yeah, because otherwise we would be duplicating the resources, using them once to obtain A, and then a second time to use A, which would be, not linear. Okay? So these rules turn out to be slightly different, right? And the other thing was in the sequent calculus before, in the left rules, we preserved the main formula, the principal formula that we applied the rule to in the premise always. So our context is monotonic. We're gathering more and more information. But here, of course, the formula disappears because when you apply Lufrel to it, that counts as a use of it. So it's gone after that. You don't have it again in the premise. Okay? Make sense? Okay, so let's complete the connectives because there are quite a few, so it's going to take us a little while. So whenever you have a binary operator like this, you have to think about what is the unit of it. So some kind of connective so that, so what we're looking for is something like, we want a tensor, some constant, let's call it 1, okay? And we want this to be, okay, equivalent to a. And in fact, we want something stronger. We want these two things to be isomorphic, which means that you have functions going back and forth and they compose to the identity, right? Okay, so we can try to figure out what that should be. So let's try to do that, okay? So we have 1, okay? So any suggestions how to proceed? So this is what we're looking for. So it should be the unit of tensor. So how should I define it? Okay. So no assumptions. And what would be the premise? What would I have to prove that? Nothing. Okay. So this is the one right rule. Okay. Does that make sense? Why don't I allow assumptions here? Yeah, it wouldn't be linear, right? Because I would have to use all the assumptions. So this has to be empty. So let's look at it. If it's a unit of tensor, it should be a zero-area version of tensor, right? So you think of a tensor with no components. So this tensor, we have two resources, two sets of resources. One goes to here, one goes to here. Here, because zero error, we have no sets of resources. Works. Here we have two premises. Here we have no premises. So it seems to work out in that way. Okay? All right. What about the left rule? What about if we have 1 on the left, we're trying to prove C? So how does the left rule work? Okay. Delta proves C. All right. So we might be tempted to say 1 is like truth, right? Because you can prove it without any premises. And we didn't even have a left rule for truth in the intuitionistic case. There was no left rule. So one thing might be, well, maybe it could be something like this. If we have that, we can get rid of it. Or it might be there is no rule for 1, right? Make sense? Because we have no elimination rule for top. We have no left rule for top. So why do we have a left rule for 1? So now we need to think again about our tests. Okay, so our test here is a cut reduction, okay, which corresponds to the local soundness. The witness for local soundness is a local reduction. So we didn't have the one left rule, okay? If we didn't have the one left rule, then there would be nothing to check because you can't have the one right rule meet the one left rule because if you don't have one, nothing to check. So if we didn't write this rule, it would be sound, okay? Make sense? No rule, nothing to check for soundness, okay? Well, what is the analog of completeness? So I didn't tell you this last time, okay? So so the local completeness is some kind of an identity expansion, okay? And in the sequent calculus, we call this identity expansion. And the way that this is formulated as a property is that if we have the identity at a compound proposition, we're trying to reduce it to identity at the components, okay? So that's the goal. So I'll show you as an example the completeness of the tensor left rule, okay? So the question is, if we have identity at tensor, okay, so this is the identity at A tensor B, can we reduce this, or expand it actually, becomes a bigger proof, into uses of the identity at A and at B? So that's the analog of what we do in natural reduction. So the question is, how do we do that? Any thoughts? So we're trying to prove A tensor B, turnstile A tensor B. And we're not allowed to use the identity at A tensor B. So how do we do that? There's two choices, right? We're in the sequent calculus, so we can use the left rule or the right rule. Okay. Why don't we use the right rule here? If you use the right rule, we'd have to split our resources, put some to the left and some to the right, okay? If we put the resources to the left, then here we have to prove A tensor B proves A, which we can't do. And here we'd have to prove B from no assumptions, which we can't do either. So we can't use the right rule. So instead, we have to use the left rule first. So that gives us A and B proves A tensor B. And then we break this up. A proves A, B proves B, and this is the identity at B, and this is the identity at A. And we have reduced the identity at A tensor B to use the identity at A and B, so the rule is complete. Okay? All right, should we check it for 1 as well? Okay. So the question is, if we use the identity at 1, okay, can we reduce this to some uses identity for the components, which means that somehow we must be able to prove this without using identity at all, right? Because there are no components. Actually, I should say expand. So can we expand this proof into one that doesn't use the identity? Okay, so we look at the rules for 1. We could start with 1 right or 1 left. Can we start with 1 right? Well, we cannot, because this must be empty. Right? And there's something here, so we cannot use the 1 right rule. So we have to apply the 1 left rule. That makes the left-hand side empty, and we're trying to prove 1. And now what do we do? Now we use the 1 right rule. And we have proven this without using the identity. Okay, so yes. So with this rule, we're also complete. Now without this rule, we would be stuck because we would, at this point, 1 proves 1, we wouldn't be able to make any progress because the 1 right rule doesn't apply, so the only way to prove that would be by using the identity. Okay, so we need this rule because otherwise these rules would not be in harmony. There would be too few left rules. Okay, make sense? Questions? Okay, good. All right, so now we define some more connectives. So we'll put these here. Okay, so the first one would be, well, let's do disjunction, right? We have a form of conjunction, we have truth, we have implication, we need disjunction, right? Or, well, there should be disjunction if you want to have something that's strong enough so we can get all of intuitionistic logic. So what are the right rule for disjunction? Okay, so you can probably dictate it to me. Okay, so we start with delta, and we're trying to prove A or B. Actually, in linear logic, this is written as A plus B. When's that true? If it's a disjunction? Right. So there's 2 rules. Delta proves A is the first, left rule for plus. And the second one is the first right rule, the second right rule, which proves B. Okay, that seems pretty uncontroversial, right? We just transcribe. There's no problem with linearity. Delta takes over. We're all okay with this? No problem? Okay, so we have to then worry what's the corresponding left rule. So we have delta, and we have A plus B, and we're trying to prove C. Okay, what should the left rule be? Anybody remember the left rule for disjunction? Yeah?
Delta A lolly B, delta B.
Yeah, not lolly turnstile because we're at the judgmental level. Yeah, but yeah. So we have A, delta and delta together with B prove C, okay? But now you should become suspicious. Suspicious. Okay, why should be you, yeah?
You're going to need to use some sort of delta time constant if you're going to use 2 different.
Okay. So the problem here with this rule, if you look at it like this, right, the apparent problem is that, oh, we duplicate delta, duplicate here and here. We're allowed to use it exactly once in a proof. Okay, it appears on both sides, so this is a problem. Okay. So let's, for the sake of argument, say, well, I have to split my resources. Delta prime. Okay? So that on the surface, it seems to be what we've always done. We have split our resources to make sure that they're not duplicated, right? Okay, well, now we need to apply a test whether these things really work, right? Okay, so let's try that. So we have a right rule meeting a left rule. So we have delta A plus B. And this is, let's take the first one. Obviously, the other case is going to be symmetric. And over here, we have delta prime, delta double prime, A plus B. Proof C, because we have the two cases. Delta prime together with A, proof C. Delta double prime together with B, proof C. So let's call this here E. Let's call this F. And let's call this D. Okay, and I do a cut at A plus B. And what's my conclusion here is going to be delta together with delta prime and delta double prime proves C. Okay? Okay, so I need to show that I can reduce this to cut on smaller formulas. Okay, and that's a cut reduction. And how do I do that in this particular case? How can I get direct evidence for C from what I have lying around? So I should be able to cut D with E, right? Because this proves A and this uses A. That makes sense? Right? Okay. So I do D, delta proves A, and I take E, delta prime together with A proves C, and then I get delta together with delta prime proves C, and this was a cut at A. Okay. Now you should be suspicious once again, or maybe even more than suspicious. What's wrong here? Okay. So somehow when I did this reduction, delta double prime went away, right? Okay, so this is very bad. Why is this very bad? We have to use each assumption, and suddenly here we're relieved of the responsibility of using delta double prime. So if you indeed had these rules, okay, then weakening would turn out to be admissible in the system, and it wouldn't be linear logic anymore at all. So we made a mistake somewhere. Okay, so cut reduction is a thing that we can't compromise on, and weakening certainly is not something you can compromise on. So where's our mistake? In the left rule, right? So we said we don't want these assumptions to be duplicated, and therefore we split them up into two pieces. Okay, that was our mistake. So what you have to realize is that when you have the assumption A plus B, and over here there's going to be a proof of A plus B, there's only going to be one proof. It's either going to be A or it's going to be B. So when the assumption is going to be used here, it's either going to be using this branch or it's going to be using this branch, but not both. Okay? And we went under the assumption that both are going to be used, which is why we split them. But only one of them is ever going to be used because either we infer it this way or we infer it that way. So really what we have to do is we really do have to split our assumptions, propagate our assumptions delta to both branches. Okay, so let's see if we do that, what happens. So we just get delta on both sides. Okay, good. Let's call it delta prime. And then here we just have delta prime. And then here, oh, okay. Now it works out. Okay, do you see this? Okay, if you didn't do the test, okay, you might have easily been led astray. But with our test, okay, it all works out. You notice that only one of these two propositions is ever going to be used, either A or B, but not both. And therefore, we have to apparently duplicate, okay, our assumptions, propagate them to both sides. Okay, does it make sense? Yeah?
I'm wondering, why could we not simply have two left rules, one with A on the left side and one with B on the so it would make the calculus non-deterministic, but would this be, so what's the problem with that?
You mean just getting A, not getting this part? Oh,
And then have another rule
yeah.
that has instead B.
Okay, so the problem with that would be that if A plus B was inferred with this right rule, and left was with the first one, then we wouldn't be able to reduce because this would prove A, but this would use A. Okay, so we would get stuck for a different reason. Yeah, we really need to account for both cases in the left rule. Okay? Yep.
So why don't you use like the exclamation point for that? Is that something totally different?
Yeah, because here I want everything to be completely linear. I want a fully linear logic, and eventually I want to add exclamation point to something completely separate from everything that I have. So with exclamation, I could define a different notion of disjunction. One can do that. But I still want to define a linear version of disjunction, and this would be it. Okay? So yeah, it's possible. But I also want to have this connective. So you agree that this is a valid connective? Okay? Good. So local reduction disappears. All right. When we have binary connective, what do we usually look for next? We look for the unit. Okay. What would be the unit for plus? I guess we call it 0. Okay. So what would be the right rules for 0? A plus 0 equals A. So we want A plus 0 isomorphic to A. What would be the right rule for 0? No right rule. Yeah, no right rule. Okay, because it's a zero-error version of disjunction. Here we have 2 rules, means we have 0 rules. What would be the left rule for 0? Okay, what's our premise? Okay, here we have 2 cases to consider. Here we have 0 cases to consider. It looks like delta is not being used. Okay, warning bells, we're violating linearity, but it's actually okay because we can never really supply proof of 0. Okay, so we're saved here. And you can check the local expansions and so on, and it still works. Okay, I'm not going to go through checking everything. So it seems like we have everything right now. We have implication, conjunction, true, disjunction, and falsehood, but there's more connectives. Okay, like Bob said, when you reduce the expressive power, okay, of when you reduce sort of the proving power, let's say, of a logic, you actually gain expressive power. We have new connectives we can say now. Okay, so which ones are they? Okay, I'm going to propose a rule, and then we figure out what it actually means. So the rule is this. Actually, let me start with the left rule. Okay, so the left rules would be the ones that I know from intuitionistic logic for conjunction. Whoops, C. And delta A with B proves C if delta B proves C. And I call this the second left rule for AND, and this is the first left rule for AND. Okay? So here's what it means. If I can use A with B, the way I can use that, I can either take the first component of it, or I can take the second component of it. Okay? So I can either, this is like conjunction elimination we had before. You can take the first projection, or you can take the second projection. Okay? And everything seems to be fine linearly, perfectly fine, no problem at all. But the question is, what is the right rule? Or the right rules for this form of conjunction? Okay, so this is problematic. Why is this problematic? Yeah, so if this is your right rule and it meets this left rule, then the left rule would pick out, in its use, will pick out B, but you only have a proof of A. So that's not enough. You also have to be able to prove B, right? because you don't know which of the two right rules will be applied. Okay? So now, oops, we're duplicating the assumptions, but is it okay? Why is it okay? Yeah, because we only use one of the two pieces. We either only use A or B, but not both because the conjunction here goes away. Right? So this is usually pronounced A with B, and it's an alternative conjunction. So A with B. Okay. And you can check with local reductions and expansions everything works. I won't go through that right now. Okay. All right. What is the unit of that? So we want something that A with top is isomorphic to A. All right. Zero area version. How many left rules should there be? How many left rules should there be for top? Okay, no left rules. Okay, so no top left. Why? Because, well, there's two rules here, but if you have a conjunction, alternative conjunction with no components, there should be no rules because you can't extract any components. And what should be the right rule? That should be the right rule, because it's just like this with zero premises, right? So again, warning bells go off. Delta is not being used here, but why is it okay? Because there's no left rule, nobody can ever use it if you provide top. Okay? All right. Okay, so let's do some examples. Okay. I'm going to erase this here, but I want to just talk you through this. So in natural reduction, we have local reduction, okay, which is an introduction followed by elimination. Here we have a cut reduction, which is a left rule meets a right rule for the same connective. Okay. Local expansion was the identity expansion we talked about. Now the global version of these properties, which we need to check, here is going to be cut elimination, which means that the rule of cut by itself is redundant. Okay. If there is a proof with cut, there's also a proof without cut. And that's usually noted both as a name of a procedure for cut elimination to get rid of it, and as a property of a logic. We say the logic satisfies cut elimination, okay, which is globally sound. And then the completeness means that identity can expand it fully, which means that the only time we need the identity, I need a different color here, is for atomic propositions P. The identity is restricted to just atomic propositions, because for all other cases you can decompose it into smaller propositions by the tests that we have, right? Identity at A tensor B can be decomposed in identity at A and tensor B. You can do that all the way through, but when you come to a variable like A, okay, which you don't know what it is, then you still have to use the identity. Okay, so you want to be able to prove, like A tensor B proves B tensor A. When you break it down to just the A, then you're stuck. You need to use the identity, so that's what you still need. So you can also think atomic propositions are just variables ranging over propositions. Okay, so the global completeness theorem says that you have a full identity expansion. Okay. Okay, so now I wanted to use this part to do some examples. Okay, so my example is going to be a vending machine, okay? So I'm going to say, if you put in $2 with your resources, okay, $1, $2 bills, you can get out, okay, let's say tea or coffee. Keep it simple. Okay, now tea or coffee, okay? So that's not a very useful vending machine. If you have this vending machine, what does it do? So it's not useful for various reasons, okay?
You pay $2 and it gives you either tea or coffee, which
Exactly. You put in $2 and it will give you tea or it will give you coffee. Well, okay, I don't know. It's the machine's choice. Okay. All right, so if you hate coffee, okay, then you might be out of luck. So this is why A plus B is also called an internal choice. Okay, because when you try to prove that, it's the prover's choice to either produce one or the other. So that's not what we want. What do we want instead? Yeah, T ampersand C, T with C. Okay, parentheses here, of course, like that. Okay, so what this says is that it's your choice between T and C, because you can apply the and left rule or the and right, in the first and left or the second and left rule. And so this is why the alternative conjunction is also referred to external choice. All right, let's complicate our examples. Oh, by the way, maybe this kind of suggests that you can put both bills in at once, right? Because you have tensor $1, tensor $1. If you want to model the fact that you have to first put in one bill and then a second one, how would we model that? We would curry it, okay? So you put in $1 and the machine goes into a state where you put in a second $1 and then you have the choice between tea and coffee. Okay? So that's a better model than this. All right, so we're making progress. Now the machine might malfunction, okay? It might not decide not to give you tea or coffee. How would we model that? So you put in $1, okay, and you put in another $1, and then the internal choice. So it either could play by the rules, it could give you tea or coffee, okay, or, okay, it could malfunction, which means what? Okay, we might hope it gives its money back. Let's first think about if it doesn't give its money back. What happens? What do you? 1, nothing more, right? 1 is a thing which is true without any resources. Okay, so you put in $1, you put in a second $1, you have the choice between tea or coffee, maybe, or it might simply malfunction, not do anything. Now we put the plus out here. Okay, that kind of means you don't really get to choose between the two, right? If you want to model the fact that you can push on the T button and then it malfunctions, how would we write that? So we get the choice between T plus 1 and coffee plus 1, and we'd have to put the parentheses like that, okay? That's maybe more realistic because you're likely to push the button before it actually malfunctions. Now, if it's actually a nice machine and if it doesn't have any more tea, it gives you your money back, how would we model that? So we put in $1, put in another $1, okay, and let's write the old version. So we have either it malfunctions right away, or we have a choice between coffee, okay, and it gives you your money back if it malfunctions. So how would we model that? Okay, so plus here, $1, tensor $2. Whoops. No, that would be a nice machine. Okay. Okay, like this. All right. So either it decides to give you tea or give you the choice between tea and coffee, or it gives you your money back. Okay. Okay. So you can kind of see how this thing works, right? You see that we need some interesting expressive power. We need a lot of connectors. We need the linear implication. We need the plus. We need the with. We need the 1. So a lot of stuff actually comes up when we try to model this kind of system. Okay. Yep.
How does the giving the money back have to work with the having to use every resource aspect?
Okay, so when you actually use this, you're kind of constructing a proof, and at the end you're left with the situation where don't have a complete proof. So what we're modeling here is basically, well, this is an assumption you can use to prove something. With this assumption, you can prove that if we have $2 to begin with, okay, and this assumption here, which is the machine, so the vending machine, together with $2, can get you into a situation where you have T or you have your money back. So that's what we should be able to prove, okay? So it's important to see how that's actually used, and this is a very good question, okay? Does that make sense? Because we have the machine here, and we have $2 like that. We can break it up into its components, and we can feed it to the machine. We don't know which of these two, so we're still left with an internal choice here. The machine chooses this, we can choose T. If the machine chooses that, we get our money back, okay? Yeah? Yeah.
But I don't understand why. I'm having a little trouble understanding why that particular set of rules leads to internal choice and the other ones.
Okay. Where's the what?
Where's the lack of like the user?
Okay. So you think about the right-hand side of the sequence. That means you're providing some service. And then on the left-hand side, you're using the service, okay? So this means somebody implementing this provides this service, so it can choose whether to give you an A or give you a B. If you're using that service, you have to be ready to handle both, okay? Now here, what the machine provides you is potentially both services, A and B, and it's ready to do so because it uses the same resources, but you as a client have to make that choice. So in informal language, we often say or. So, you get tea or coffee, but it's not really a disjunction. It's a choice. The or is a choice between these two rules, but it's a conjunction because the provider must be ready for either choice. Okay, so that's kind of our usual word or, when you try to transcribe it into various logics, doesn't always translate into an or. Yep.
Is there some implicit idea that service doesn't actually use the resource until the user asks for the service?
Right.
Otherwise, you have to use the same resource twice to pre-build A and B.
Right. So this is an excellent point. So what happens is, how does computation, well, I say computation now, but how does the system actually evolve? It evolves by cut reduction, right? When the right rule meets the left rule for the same connective. And it happens precisely when you reduce a cut, for example, between providing both of those and somebody consuming it, okay? So cut reduction is the engine of change of state. Or as I'd like to say, cut reduction is the engine of computation. Because that's my next point now, okay? There's still other things wrong with that, okay? Anybody want to suggest anything else that's wrong with that? Yeah? Yeah.
Just more a question. So you want to model the fact that at any point the user of the machine can decide to retract the dollar and just use it. So we would have to add the end
Right.
for the last linear implication.
Yeah, so it gets more complicated if you want to, but you can do things like that. Yeah. Yeah?
We're trying to model resources here, but if you think about how the machine works, it's not actually it doesn't actually consume the dollar. So it actually consumes water and instant coffee powder or whatever, right?
Yeah.
Where in this view, the money sort of vanishes into thin air. And you haven't really maximized revenue.
Yeah, so that's an issue, right? So in fact, I have worked on a modal extension of this where you have, so the slogan is that, okay, so back up. So in modal logic, you can talk about knowledge, right? So we talk about knowledge of principles of various propositions, right? And a linear form of knowledge is actually possession, okay? So it's knowledge that you have, but you can give it up. But it follows the same laws as knowledge in other ways. So you can extend this modality to capture this idea of possession, and then you can model the transfer of the dollars from one to another and so on. So yeah, so you can do that, but you have to complicate your logic to account for that. Yeah, I mean, the thing which I want to point out here is that this vending machine evaporates after you use it once. okay? Okay. So it's of limited use, okay? So anticipating what I might say later, you might say, okay, well, we can use the vending machine as often as we want. Okay, so that makes it slightly more realistic, okay? So we do need some modalities because certain resources are keeping persistence, okay? That's still not a very good model, but I don't think I have time today to give you other ways of constructing these things, okay? So what I want to know now is move on to a model of computation derived from that. Okay, so let's do this over here. Okay. Okay, so what we're used to so far is the following. Let me just remind you. Okay, actually, let's put it here, because then I can cover it up because we don't really need it. Okay, so we have a context gamma, and we have a natural reduction proof of A. And the way you get a programming language is that you change your gamma. Okay, so let's put it this way. A1, AN proves A in natural deduction. Okay, and you get out of that, these actually become, okay, variables, each assumption variables. And then again, in natural reduction, you say M is a proof of A. And we have seen there is a sort of an isomorphism between the terms M and the proofs of A. So we can extract the term from the proof, and using the proof, we can reconstruct, using the term, we can reconstruct the proof, okay? And computation arises when introductions are met by eliminations or constructors are met by destructors, okay? And we have local reduction driving computation. Drives computation. Okay, and if you look at that, if you remember, the critical part of that was something like this. If you have lambda x dot m applied to n, then we locally reduce that in n, substituted for x and m. So if you look underneath the connectives to the judgmental principles, the key is substitution. What drives computation really is substitution. Even though you might implement it in different ways, building closures, whatever have you, but in some sense, the driving force in functional computation is substitution underneath. Okay. Now here we're going to take a different attitude. Okay, I'll write it here so it stays up. Okay. So instead of having a term m here and having these be variables, we make each of them a channel. Okay, so we have a channel 1 has type A1, channel n has type AN. And then here, instead of a term, we have a process. So instead of a function that computes, we have a process. And instead of just here, we say that we actually also have a channel on the right-hand side. And the reason is that processes are connected with each other via channels. So we don't just compute a value and return it, but we communicate with the outside world along this channel here and along these channels over here. So this is what we're going to now use delta for. And the point is that the process P, it uses these channels, C1 to 3n, and it provides this channel over here. Okay? And the proposition, the linear proposition, is what's called a session type. And the session type gives you a prescription how this process has to interact, okay, along this channel. It gives you a prescription, a protocol for interacting along this channel, and also protocols, of course, for each of these to interact along these channels. Okay. So now we're going to go, in the rest of the lecture, what we're going to do is we're going to go through the various constructs and see what's their concurrent meaning, kind of extracting a programming language, okay, from doing that. All right, so let's start with cut, because this is somehow, cut is part of the key of this. So it's very, very important to understand the notion of a cut. So we write the cut rule again. So we have delta, okay, and we have A, and we have delta prime together with A and we have C. And then in the conclusion, we have delta together with delta prime, and okay, we have C. All right. So let's say that we have some process P here, and process P offers along C this service A. So it provides a service A, and this process here actually uses service A. Okay, and I'm going to use the same channel name so that both processes communicate with each other along this channel. Okay, and there's going to be some process Q here, and Q is going to, okay, let me rewrite this into D. It's offers some service. Okay, so this is not going to change. And here what we have is so something like this. Let me write it out explicitly like that. Spawn P and a continuous Q. Okay, so the operational reading of this is this process here. Okay, spawns a process P, which provides service A along C, and then continues as Q using this new channel that's actually provided by P. So in the pi calculus, if you know about the pi calculus, you write this as there's a new channel X, new channel C, which is private, and you run P and Q in parallel. Okay. So this is a little more semantic. This is more syntactic in the way you think about the meaning of this connective. Okay. So cut corresponds to spawning a new process. Okay. Does that make sense? Probably not. Okay. So if you can formulate a question, otherwise I'll plow ahead and maybe over time it'll make more sense. Yeah?
Could you say in English again what the notation C output and C?
Okay. So the process P, so this is a process here. It provides a service along one channel. Think about the process of being the vending machine, right? The vending machine provides a service. The type here, okay, so the channel is one way to interact with the process, okay? And the type prescribes how the interaction is supposed to take place. Okay, so if you think of the vending machine as a process, the vending machine process would say, along some channel C, we provide the ability to give me $1, give me another $1, and then I'll react in some way. Okay, so I provide a service, but the vending machine doesn't have to, operate in a vacuum. It can use some other services because it can have multiple processes plugged together interacting with each other. Okay, so it will use other services, but it provides service along C. So in a functional setting, we don't have that because we have a term here, and all we do with the term, we evaluate it down to a value, then we're done. But if you have a process, it has to continue to interact with its environment. And so we name the channel along which it interacts with its environment. Okay? All right. So cut corresponds to process spawning or process composition. So this is kind of the semantics of the syntax. Okay. Okay. Identity is trickier. Okay, maybe I'll discuss identity later. Okay, maybe I'll just discuss some of the connectives. Okay. Okay, so let's see. Let's do linear implication, right? Because it comes up in the vending machine, right? Okay. So the question is, if you have a context delta, okay, and we provide service A implies B along that channel. Okay, we have delta, and let's call this D:A. And then we provide B. Okay? So again, think about the vending machine. Any idea what this might mean from the process perspective? Okay, could you say it again? I think it's...
You give it a process that produces A, it gives you a process that produces B.
Excellent. Okay, so you input a process that produces A, and then you continue by providing B along the same channel. Okay, the only difference to what you said is we don't actually pass processes around. What we pass around is channels. So handle is to interact with processes, but not the process itself. The process itself is running somewhere, interacting with its environment. Okay, so this is some kind of an input. So we say that we receive D along channel C and continue with Q, and Q is going to do this. Okay? So it corresponds to an input along a channel, which is true, right? From the vending machine perspective, if you have to input $1. $1 is really just a handle on a process by which you can exchange $1 in future time against something else, right? Okay, does that make sense? It's not too surprising, actually, because as a function, it means function application. So you give the function the argument, and it computes the result. Here, you send the argument to the function, and it continues to offer along the same channel some more interactions. Okay, maybe another input and maybe an output. Okay, make sense? Yeah? Yeah, that's right. If you only do input, then it's sort of like you pipe, you input, 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 okay? But we'll see, because we can alternate input and output, it's more complicated, right? Because information can flow in both directions, as we'll see, okay? Yeah?
Is there anything special about that semicolon you're using, or?
Well, this is supposed to suggest that this, then that. Okay, so if you're using a semicolon in imperative language, I'm using this kind of a suggestive notation. But it just says, do this, receive a C, and then continue as Q.
Like monadic bind, right?
Yes. If you're used to function programming, it's a monadic bind operation. But I wanted to hide that fact from you.
Sorry.
It's okay. You can never have too much information. All right. Okay, so wait. We only did one half of implication, right? So this is the right rule, which is an input. Now, what does the left rule have to be? So let's think about that. So in the left rule, we have a context, delta, delta prime, and it has in it C, A, or B. Okay, I'll need a lot of room for that, probably. And it itself is going to be, okay, something like that. It offers some service to the outside. Okay, so let's try to fill in the pieces. Actually, before we fill that in, could everybody guess? If this is a receive, what would the left rule have to be? It would have to be a send, right? Because computation happens when the right rule meets the left rule. So if the right rule wants to receive, right, the left rule has to send so that they can communicate properly. When they're hooked up to the cut rule, right? At one end, there's going to be process P, which provides the service. At the other end of the channel, there's going to be a process Q, which uses it. And so they have to have exactly complementary action for computation to be able to proceed. So it's going to have to be a send. So we know that much. But let's figure out more about that. Delta prime, we prove A. And delta double prime, okay, we prove E. This is still along this channel, okay? So we want to send. And along which channel here? Obviously along channel C, right? So this process here does not, in this step, it interacts not along the channel that it provides, but it interacts with the channel that it uses. So this channel and all the other channels in delta prime and delta double prime, they're going to be dormant. You're not going to do anything with that at the moment. We just send along C, okay? The question is, what do we send along C? Okay, so we can send A because A is a type. Okay, so the next thing would be, okay, we have something here. We have a P, and P offers service A. So the next thing might be, I might want to send, oops, this shouldn't be C. This should be D. Okay. Next thing I say we want to invent P, but it's not P. Why is it not P? We never send processes. What do we send instead? Channel. So which channel should we send? D. Okay. And after we do that, we continue as Q, and Q is the channel here. Okay? That's not quite right. What's the problem here?
In the assumption on the right, you should be able to use the process if that's it.
Right. So that's one problem. Right? So what happens is when we send D along this channel, then C from then on is going to offer B. Right? Okay, good. So now we get to use the same channel. It changes state because we pass it a channel of type A. Now it's going to have type B. Great, we can use that. That's good. So that takes care of one problem. There's still a problem. Okay, what happened to P, the process P, here? Okay. Okay, so we can't do that. We can't just send D. We actually have to spawn P to provide the service. So the way we write this is like that. Okay. So we spawn the process P, which will provide service A along D. We pass that channel to C. Okay. And then we continue. Now we can use C at type B. Okay. So in the pi calculus, what would this be? So we create a new channel D, and we send along C the channel D, and then we execute P and Q in parallel. I think it may be this. Okay. So we create a fresh channel, okay, D, which nobody else knows about except P, and P provides that for us. We send that along C, and then P and Q continue in parallel afterwards. Okay. Operationally, if this is a piece of syntax, what we do is we spawn a new process P that offers a new channel, which we then send along C, and then we continue as Q. Okay? And now these two fit together, and they execute in the correct way. So in fact, the computation step that happens when these two processes interact, one that receives and one that sends, is exactly the cut reduction which I showed you before. The cut reduction reducing a cut at a compound time to two cuts at smaller types. Okay? I can't show you that now because I won't get through all the connectives that way, but you have to trust me on that. So the engine of computation here, okay, in this setting, is communication, and communication is modeled as cut reduction. And it's very different from substitution because substitution happens in one big step. You substitute n for x and m, like it's one big step. You go through all of m and you substitute n everywhere. Communication is cut reduction is a tiny step because you reduce only a cut at A tensor B into two cuts very locally. So computation is much more local, which is why the sequence calculus is a good match for describing concurrent computation, much better match than natural deduction. Okay. Yep.
So if you're proving some lemma about a concurrent system here, are you proving some sequence of message sends and receives, or can you do something more general?
Okay, so the question is then essentially how are these little processes embedded in a programming language, right? And there's no unique answer to that. You can do this in many different ways. In some sense, which I currently think is the best way, is that you encapsulate this in a functional language in a monadic form. And then this is indeed a monadic bind, okay? And then you have all of the functional language around you. And inside the monad, you have concurrent computation that sends and receives. And once we have gone through all the constructs, you'll see the remaining constructs of the language. Okay? So, but basically, it turns out every cut reduction corresponds to a send or receive of something. Okay? So every cut reduction is actually a communication. So one of the slogans, a cut reduction in linear logic corresponds to communication when the processes execute. Okay? Okay. All right, let's do identity while it's up there. Okay. So what does the identity do? Okay, so we're offering C along A, and we have D along A, and we have the identity of type A. Okay, so think about it this way. We have to write here a process which claims to provide A, and it can use D of type A. Okay, so what we do is essentially we forward any client request to D. So we say we implement C by D. Okay, something like that. And we terminate because we have done our work. Okay, we have hooked up the client here on the other side, right? On the other side of the cut rule, there's a client with D. Okay, so they don't know that they're no longer talking to us. They're now talking to some other provider that we're using. So this is, we usually call this forwarding. So we forward the request, okay, and we terminate. So in cut, we spawn a new process, and with the identity, we terminate the process. So they're kind of inverses of each other, which is a well-known sort of theme in proof theory, that cut and identity are inverses, okay? So we have done our work, okay? So in a picture, if you want a picture of that, okay, I usually draw processes P like this. It uses many channels, and it provides one channel over here. So that's what P looks like. Actually, I should write it the other way around, so it's consistent with my notation. So I provide here along C, and I use here along channels C1 through Cn, and this is a process P. Okay. So for forwarding, the process says use D to implement C. I only have one process here, which is only one channel here, which is D. And I offer C over here. And this evolves essentially, it becomes by local reduction, by some kind of reduction, this picture, okay, where this provider over here, I don't know who it is, and I identify C and D over here. And I terminate essentially by just plugging these two wires together. Okay. So that's a concept that doesn't exist in the pi calculus, and it's missing from the pi calculus. Okay. And once you do it from a logical perspective, you realize, oh, it should have been there. Okay. Because it's a very important operation. Once you start writing programs, it becomes even more obvious. Okay, but let's fill in. We have hopefully enough time to fill out our entire board here with all the different connectives. Okay. Yep. Which last part?
What pi calculus is missing in.
Oh, pi calculus does not have a forwarding construct. Okay, so because it's untyped, you can kind of program something that behaves similarly, sort of in the more primitives, but it's not given to as a primitive operations. And if you look at other languages like concurrent ML or joint calculus, the forwarding is missing, and it makes it difficult to program in. Once you have this language to program in, you realize that it's a very important thing to be able to do. Now, I can't show you any interesting programs. Today, I can really only show you sort of the pieces of the language, and you can read up with examples. Okay. Okay, everybody on board? So let's try to figure out what the other constructs mean to get a more complete language. So what's important to keep here? Everything. Okay, all right. Okay. So okay, let's do external choice. So before I even start, you should maybe be able to tell me what external choice is. Should external choice correspond to an input or an output? A receive or a send? External choice corresponds to a send? Well, it has to be a receive, right? Because you're offering the external world a choice, so you have to receive because it has to make a choice. So it has to tell you which of the two possibility, okay? So this is the provider, and the client has a chance to select between the two. So it has to be a receive because you have to see which one the client selected. Make sense? Okay, so here's how it looks. So in delta, we offer A with B along the channel C. Okay, and we have here A, and this is still along C. And here we have, and this is still along C. And this is some process P, and this is some process Q. Okay? Okay, so now we have to receive along this channel C something. Okay, I need some more space. What should we receive along channel C? Any nominations? How much information do we need? 1 bit, right? Just which one, left or right? So 0 or 1. But instead, I'm going to write it like this. So we have a case here, depending on what we receive along the channel C. It could either be an in left, in which case we continue as P, or it could be in right and we continue as Q. Okay? Okay. You could also think about, instead of notation, what you receive along C is either pi 1 or pi 2. Okay? If we receive pi 1, which is a token, then we continue with P. If we receive pi 2, we continue as Q. But I'm going to call it in left and in right because really it corresponds to a case construct. Okay? Make sense? All right. And so now what has to be the left rule? Let's start one of them. So I have C, A with B. And over here I have D colon D. I don't care about. Okay, so the one left rule says, well, I picked the left part. So this is the width right, and this is the width left 1. Okay? So what should we do in this case? Right, exactly. So we send along channel C in left, and then we continue as Q. And here we have Q. Okay? And then if this was the second width left rule, and we had B here, then what we would do here is send in right. Okay, and the provider would correspond and transition, actually let me call this R, transition to either P if it receives in left, or it would transition to Q if it receives in right. Okay, so you could write down now the operation semantics rule, right, if you want, and it would be something like this. So if you have a case of receive along C, from one in left, go to P, in right, go to Q, and you have that, and somewhere else you have executing a process that wants to send along C, in left, follow that by P, so maybe I'll use a different notation. These are separate processes, but they share a channel, okay? Then you can make a transition to, what do I transition to? This should be R. Okay. So this transitions to P here, and this other transitions to R. Okay. This is what sort of an operation semantics, which I'm not going to give you, but just give you an idea. So we have this is one process, this is another one. This one wants to send along a channel, this one receive along a channel. If this sends in left, then this continues P, and this just continues at R. Okay. And what we have to show that the whole language makes sense, we have to show that P and R now still continue to agree on the type of the channel C. So they don't get mixed up in their protocol. Why is that? Well, you see here the AND left rule gives you A, and P will exactly provide A along this channel if it receives in left. Okay? So that's the contents of the cut reduction, is that the type of the channel changes, but the two sides still agree on it. Okay? So therefore, this is a sound rule, okay? And the language has something called type preservation, right? Make sense? All right, good. So that was the external choice. Now, what is the internal choice? what would be our interpretation of internal choice? This one here. I'm not going to write it out because I'm going to run out of time, but what would this do, this construct? This would send, and what would it send? It would send in left, right? The provider makes a choice, so the provider has to send. So the provider would send in left and then continue with P of type A. What would this do? It would send in right. And what would this do? Okay, it would receive along this channel and do a case. If it receives in left, it will continue like this process. If it receives in right, it would continue like this process. Make sense? Okay, good. What about the zero right rule? Well, it has nothing to do because it doesn't exist. Okay, which is good. What about the zero left rule? Yeah, so it would receive along channel C, which has type 0. If it ever receives something, it would abort, right? Because, well, there's no cases to pursue. But obviously, it should never be, in a well-typed program, it should never be able to receive anything, right? Okay? Okay, so let's see. Oh, we need 1. 1. What does 1 do? Okay, so that actually I want to write out. So we saw internal choice, external choice. Okay, so the right rule is in the empty context, C:1. Okay, what does the process do for the one right rule? Could you say it again? I couldn't quite hear it. Yeah? Yeah, so it sends along 1, along C, some kind of unit value. Okay, or some kind of token that says, okay, we're done. Now it has no continuation, so this is its final act, right? It sends, I'm done, and terminates. So actually in the programming language I have, we call it, we close the channel C, okay? But what closing means, we send a message, which is just sort of a token, okay? Now what does the left rule do? The corresponding left rule, C:1, and here we offer this, okay? And in the premise, we just have delta, and the continuation is just going to be some Q, okay? So what would you do here? Right, so we wait for channel C to terminate, okay, and then we continue as Q. And so wait actually is, if you want to do something similar, is the receiving end. So we say end gets receive along C. In the actual language, say we wait, receive along C. We wait for C to terminate, and then we continue as Q. But waiting is actually receiving a message saying that the process on the other side is terminated. Okay, make sense? Okay, I think only thing that's missing is tensor. Okay, so what should tensor do? What should A tensor B do? Yeah?
Receive two elements from one channel each and return a pair.
Yeah, that was what you would think, but that's actually not what it does. And actually, this is a very good point. The reason, I mean, linear logic has been in existence for a long time, right, since '86. The reason that this computational interpretation via Curry-Howard isomorphism was being missed was because of the weirdness of tensor, okay? So what a tensor actually does is exactly the dual to what the client does when this happens. So it sends a channel, a new channel, C of type A, along this channel here that it provides, and then continues as B. And so the client now expects to input a channel of type A, which it can then use, and it can still continue to use that same channel at type B. as it continues. So there's an asymmetry in the way that the tensor is interpreted. Okay. Okay, so let's write down the summary of the interpretation, and that's the end of my 5 lectures. Okay. So I don't have the time to show you how Bang works, okay, unfortunately. But I think at least, hopefully, I can get the idea of this across. Okay, so C:(A), B means receive D:(A) along C, and then continue as B. Okay, C:(A) tensor B means you send some new channel D of type A along C, continue as B. Okay, C:(1) means you terminate, and you terminate by sending an end message. C:(A) with B means you receive in left or in right. Continue as A or B, depending on which one you receive. C:(A) plus B means you send in left or in right, and continue as A or B, respectively. Okay? So those are the purely linear connectors that we have. Okay? So something of this type, okay, it's more complicated to explain, but roughly what it is, it's a persistent service. Okay? So that means you can get as many copies of A as you want. And the way you initiate interaction with the process that offers that is you send it a new channel of type A. It'll spawn a new process, and you communicate now in a linear fashion with that instance of the process. And you can do that as often as you like, because this process can be replicated. That kind of, at this level of abstraction, makes sense? Okay, you can get arbitrarily many instances of that service. Okay. All right, more points of question or discussion. Yep.
The one type of the program in the thing, but I guarantee that every process, whenever it wants to receive can, and it's always someone listening when it's done.
Yes. So that's right. So what you get as a result of this is, first of all, that everybody applies the rules, which is called session fidelity. So if all the programs are well typed and the program waits to receive, okay, the client will send. Okay. Okay, so that's the corresponding to type preservation in a functional language. We have a progress theorem, which is that in this pure language without recursion, okay, if somebody is waiting to receive, it will eventually get something. The client will eventually send. Okay, so you have kind of a progress theorem as well. Yeah, those are the main theorems that you have, right? Everybody continue to play by the rules, and you will have global progress.
Linearity also sort of says that there's only one sender and receiver per channel.
Yeah.
So the operation semantics would be simple.
Right. So what you have is that every linear channel has one sender and one receiver. Replicable channels have potentially multiple clients. Okay. Because many of them could request another instance, and that's okay. You can have contention there, but for the linear channels, you have 2 exact endpoints, and it comes from the fact that you have somewhere channels are plugged together with the cut rules, and the cut rule has one provider and one client. So there's an implementation of all of this, and the syntax is close to what I showed you, which is called SIL, Session-Typed Intuitionistic Linear Logic. Okay, and you can play with that, and we have a bunch of examples like some concurrent data structures like concurrent queues, priority queues, various sorting algorithms, Cipher Veritosthenes to generate prime numbers with parallel processes, binary counters where every process holds a bit, and you communicate carries. So any, a fairly large variety of kind of concurrent programs that you can write in this language. And you should be able to, if you have OCaml, there were instructions sent or posted on the website on how to install it. And there is some documentation. But there's lots of example programs. And if you have questions, I'm still here today and part of the day tomorrow to answer questions. It's fun to play with. Okay. More points? Yes?
So at the beginning, you sort of quickly move past that full cut elimination sort of corresponds to normalization.
Yeah.
So I can see that I can see motivations for that or studying that when you like look for a computational point of view. But is there a merit in that just like purely from the logical system point of view?
So from the logical point of view, normalization means you create a normal form. A normal form here just means that it's a verification, right? Okay. So that's a little different from functional evaluation, because in functional program evaluation, you stop when you get to lambda. So it's full normalization. The whole term is normal. There are no redexes anywhere in the term. And that corresponds to full cut elimination here. Okay. Now, full cut elimination may not actually apply because there is something similar in the sense that underneath prefixes, like in the pi calculus, if you're familiar with them, you don't necessarily reduce. You wait for a message before you actually reduce. Okay. So normalization corresponds to full normalization to full cut elimination, and the strategy is also reflected here in some way that you don't go under prefixes until we receive answers. Yeah. Yeah.
So would cut elimination for this mean that you could have done everything on one thread instead of spawning new threads?
No. So cut elimination means you spawn many threads, but they all eventually terminate if you start with this. So if you start with an empty context and you have some program P which offers along some initial channel something of type 1. So that's the concurrent analog of having a closed term that you evaluate. Okay. And this makes many steps, spawns many processes, okay, but after many, many potential reductions, eventually P will be at the point where it wants to send, where it wants to close C naught.
But I mean, cut elimination as like, you didn't have to use the cut rule at all because it's admissible from the rules that you have already.
Yeah.
You can write the program without spawning any threads.
No, you cannot, because if you cut elimination means that a cut-free proof corresponds to a program which will never do anything. Because computation arises from cut reduction. If there's no cut in your proof, then there's no computation. So it's writing like a normal term in the lambda calculus. If you want to reduce a normal term, you're out of luck. So if you write a normal term, no computation will ever happen. Okay. So cut elimination just means that your programs will always terminate. Okay. Yeah.
Can you give a little bit more intuition why the tensor, its computational interpretation is asymmetric?
Okay. Maybe not. I don't know. Okay. So. Okay. Okay, so when you have when you give a computation interpretation, you offer along some channel C. Okay. So the question is, so you could give a symmetric interpretation if you wanted to. What that would do is it would spawn two new processes. E. Okay. One would offer D and one would offer E. But what about the counterpart of that, right? So it would be tricky to figure out how to write the left rule, how to decompose that and make everything work out. So what we do instead is the following. We arbitrarily designate this one. We could have designated this one, but because we like to read type from right to left, we say this is the continuation. Okay. So if we start, if the process P offers A tensor B, it will send the D, which is new, which has type A, and continuous B. And then here, the C, which is here, has to receive some D of type A, and then C will have type B here for the continuation. That's the process we already talked about. Okay. Otherwise, every time you have a tensor, you would spawn 2 new processes, and you would have a proliferation of processes everywhere. Okay. So it's asymmetric, but what we find out, by the way, is that A tensor B is still isomorphic to B tensor A. What that means is you can write a processes going both ways. In fact, they're the same. And you can compose them to the identity. So it actually doesn't matter which one you do it, so that the expressive power really ends up to be the same because of this isomorphism. Yeah.
It doesn't matter from the point of view of the consumer, though, that those are the same thread, right?
That this is the same thread. Well, yeah, so
It would just look to the consumer like, okay, now I get 2 different threads. One produces A's and one produces B's.
right.
It doesn't matter to them that the one that produces B's is the same as the one they got for the people.
True. We would just have the construct here would be more complicated because it would have to somehow consume C and then expect to.
Get new names.
Yeah. Right. Yep. So you could do that. Okay. Other questions or point of discussion? Oh, I should give a reference. So this idea for all of that goes back to a paper by Kairos and myself in 2010. And our first instantiation of the idea was slightly different from what I presented here. We didn't get it 100% right, but we came pretty close. And since then, I think the worked out version of all of that is my student Bernardo Tonino's thesis. Actually, he's a joint student between that, which just came out. Okay. In which he describes not only this and the Curry-Howard isomorphism, but also the implementation inside a functional language where we have a monad for concurrency, where all these constructs are basically available to you. Okay. All right. Well, thank you very much.